We're going to take a look at 4C from the midterm now. So this is a tree recursion problem, and the way we can look at recursion is always start with the base case. So here we see that the bottom line, the lowest level of leaves, are all zeros in a resulting tree. So we're going to go ahead and write value equal to 0 in the base case line to support that. This is the simplest case. When there's nothing, when the node has no children, we're going to set our value to 0. So I'm going to go ahead and draw out the original tree, and we can talk at a high level about what we're planning on doing. So to do the sum descendants, we're going to take the 3 and 5 and 7 and 9 and set those all to 0. And then we're going to take the 4 and set it to the sum of the two descendants, which are now zeros, but previously were 3 and 5, which is 8. We're going to do the same thing for the right subtree, and then finally we're going to add up the all the descendants to get the final number. So it's going to be 4 plus 8, 6 is 2 children, plus the sum of their descendants, which we just found out was 8 and 16. So now we're going to start looking at the else case, now that we talked about it at a higher level. So I'm going to initialize two variables, left sum and right sum. And that's going to kind of represent traversing down the left-hand side of a tree and the right-hand side of a tree. Not traversing, well, recursing. So once we initialize those variables, we're going to think, okay, typically we're going to look at this and say, okay, when the left-hand side is null, we're going to do something, right? We're going to add to our left sum maybe. And then when our right-hand tree is null, we're going to add to our right sum. And then eventually we're going to add up the left sum and the right sum to go together into the top node. So I'm kind of creating a framework here of when left is equal to null and when right is equal to null to kind of build a shell. And so I'm going to go ahead and implement what I just talked about and say, okay, left sum is going to be left.sum descendant. So that's a recursive call, and whatever that returns will be what left sum is, its value. And symmetrically, we're going to do that also for right sum. So now that we have this down, we have one more blank on the bottom, and this is where we're going to join left sum with right sum. So what we want to do is set the new value of the node to the sum of left sum and right sum. It's to children node in a subtree, or all the subtrees on the left and right hand side of the bigger tree added up together. So now let's check our code and see how this works. So we're going to call it with 6, right? Sum descendants. I abbreviated it with SD. And so we're going to have a kind of left sum and a right sum. So first we hit the left. Left is not equal to null, so we're going to recurse with left.sum descendant. So the left child of 6 is 4. That also is going to have a left sum and a right sum. So we're going to look at the left sum and see that it's going to be sum descendants of 3, which is the base case. And so we're going to return our old value, which is set to 3, and then value is going to be set to 0. So we can cross off the 3 and put a 0. And then it'll return 3 into the left sum of the call for sum descendants 4. We're going to go to the right side and see that that also hits the base case. So we call sum descendants 5, it's going to return 5, and 5 will now, the value will be set to 0. And so for the sum descendants call to 4, we can put in 5 because it will return a 5. So now that we've traversed the left and the right side of the sum descendants of 4, we're going to hit this bottom part. And it's going to involve the return values that we just got, and we're going to set old value first to 4 because that's the call that we're on. And then we're going to go ahead and add up the left sum and the right sum to be 8, 3 plus 5. and then we're going to return the old value plus value. So it's going to be 4 plus 8. And so that return value will then go to the left sum of the call in our recursive stack to some descendants of 6. So we're going to set that to 12. So now we have to go down the right side. So we're going to have a call to some descendants of 8, and the left side is not null. So then we're going to go ahead and call some descendants on 7. And so this will hit our base case. So 7 will become 0. And then we're going to go ahead and return 7. So then the left sum for the call of some descendants on 8 becomes 7. And so now we have to look at the right side. And so we're going to have some descendants of 9 because that is the right child of 8. And that's also going to hit the base case and return 9. And 9 is going to be the 9 currently in the tree, the value will be set to 0. So now we can go to the bottom case, similarly like what we did on the left side, once we traverse the left and right side of the call to some descendants of 8. So old value is going to equal 8 because that is the current value of the node. It says old value equals value. And then we're going to send value equal to left sum and right sum. So 7 plus 9, 16, and we're going to go ahead and return 24 because that is 16 plus 8. So now that we have both the left sum and the right sum for our original call, some descendants of 6, we can go ahead and hit the bottom part of the code for this case as well. So that's going to require setting old value to the current value, which is 6. And then we're going to set value to the sum of the left sum and the right sum, which we want to be 36. And lo and behold, 12 plus 24 is 36, which is the answer that we wanted. And then we're going to go ahead and return 36 plus 6, which is the old value plus the new value. So we return 42. It doesn't really go in our tree, but that's the value because this equation does return an integer. That's what we would get. So if we go ahead and update the tree really quick, sorry, I kind of forgot to do that as we went. We would put in 8, which we got 16, and then at top 36. And that looks exactly like the expected outcome. And we know this will scale because of the recursion, right? So we got our good answer. I hope this video helped.